Let x1, x2 and xn are the independent and identically distributed sample size n is greater than equal to 2 from n mu sigma square, then first x bar is equal to n mu sigma square upon n. Second, x bar and s square are independent. Third, nSsq upon sigma square is congruent to x square n minus 1. First, we are to show that x is congruent to n mu sigma square n. Since x bar is equal to x1 plus x2 plus so on xn upon n, therefore the moment generating function for x is given by mx t e is equal to e t x bar is equal to e square bracket starts e raised to power t bracket starts x1 x2 so on xn upon n is equal to e small e raised to power t x1 upon n e bracket starts e raised to power t x2 upon n bracket close so on e is bracket starts small e raised to power t xn upon n bracket close is equation 1. Since x1 and x2 and xn are the independent variable, again since x1 x2 and xn is a random sample of size from n mu sigma square, therefore we have mxit is equal to e raised to power ut plus half sigma square t for all values of I varying from 1 to 3 so on, and thus e bracket starts e raised to power t xi bracket close is equal to e ut plus half sigma square t square for all values of I 1 to so on, and this is equation 2. Now putting 2 in 1, we get m of x t is equal to bracket starts e raised to power ut upon n plus half sigma square t square upon n square bracket close raised to power into raised to power n is equal to e ut plus half sigma square upon n t square, which shows that x bar is congruent to n mu and sigma square upon n. Second, here we are to show that x bar is equal to s square are independent. For this, first we consider the problem of the distribution of s square, the variance of the random sample x1 x2 and xn from the distribution of n mu sigma square. Let y1 is equal to x bar, y2 is equal to x2 minus x bar, y3 is equal to x3 minus x bar, y and so on, yn is equal to xn minus x bar. This is equation 3. By the joint probability distribution, the corresponding inverse transformation is equal to x1 equal to y1 minus y2 minus y3 so on, yn x2 is equal to y1 plus y2, x3 is equal to y1 plus y3 so on, xn equal to y1 plus yn. Equation 4 has Jacobians n, but I 1 varying from sigma 1 varying from 1 to n x I minus u mu bracket close whole square is equal to sigma 1 to n bracket starts xi minus x bar plus x bar minus mu means x bar plus और minus करेंगे is equal to sigma 1 to n bracket starts xi minus x bar और स्क्वेयर को जो है डिस्ट्रीब्यूट कर देंगे इसमें 2nx वाली टर्म जो है कैंसिल हो जाएगी इस यहाँ पर हमारे पास रिमेन रह जाएगा i माइनस एक्स बार स्क्वेयर प्लस n एक्स बार माइनस म्यू एक्स स्क्वेयर सिंस 2x bar minus mu sigma I varying from 1 to n xi minus x bar is equal to 0. ये वाली दिस टर्म विल बिकम्स इक्वल टू ये वाली टर्म जो है 0 हो जाएगी फिर हमारे पास सिर्फ यही टर्म रिमेन रह जाएगी. Therefore, the joint probability density function of x1, x2, xn is then bracket starts 1 upon sigma 2 pi bracket close raised to power n exponential square bracket starts sigma bracket starts xi minus x bar square upon 2 sigma square minus n bracket starts x bar minus mu bracket close whole square upon 2 sigma square. Equation 6 here x bar is equal to x1 plus x2 plus xn upon n minus infinity is less than s xn less than plus infinity I is equal to 1 to so and thus the joint probability density function of y1 y2 and yn with y1 equal to x bar and x1 minus x bar equal to y2 minus y3 so on yn is given by n bracket starts 1 upon sigma square root of 2 pi bracket close whole raised to power n exponential bracket starts minus y2 minus y3 minus yn bracket close whole square upon 2 sigma square minus sigma 2 to n yi square upon 2 sigma square. First term is containing this xi minus x bar and second term is containing yi square upon sigma 2 sigma square here also 2 sigma square and third term containing y1 minus n y1 minus mu whole square upon 2 sigma square where minus infinity is less than yn is less than plus infinity I varying from 1 to n. Equation 7 from 7 is the product of the probability density function of y1 and n namely y1 namely 1 upon square root of 2 pi sigma square n exponentials bracket starts minus bracket starts y1 minus mu bracket close whole square upon 2 sigma square upon n bracket close minus infinity is less than y1 is less than plus infinity and the function of y2 y3 and yn. Therefore y1 must be independent of n minus 1 random variable y2 y3 and yn, that is the function of y2 and y3 yn is the joint probability density function of y2 y3 so on yn. This shows that y1 is equal to x bar, thus n y1 minus mu square upon sigma square is equal to n bracket starts x bar minus mu whole square upon sigma square is equal to w1. This is equation 8 are independent of bracket starts y2 minus yn square upon square plus sigma 2 to n yi square upon sigma square is equal to sigma 1 to n bracket starts xi minus x bar whole square upon sigma square is equal to w2. Equation 9, which gives the required result. Third, since w1 is the square of the standard normal variable, if it is distributed x square equals to x square 1 also v shows that w is equal to sigma 1 to n xi minus mu upon sigma square is equal to w1 plus w2 is x square n. Since w1 and w2 are independent, and therefore we have ETW is equal to ETW1 and ETW2 are equivalently. We have 1 minus 2 n upon 2 raised to power n upon minus n upon 2 is equal to 1 minus 2t raised to power minus 1 upon 2 e raised to power tw2, where t is less than 1 upon 2. Therefore e raised to power tw2 is equal to 1 minus 2t whole raised to power minus n minus 1 upon 2, where t is less than 1 upon 2, and hence w2 is equal to n s square upon sigma square is xi square upon xi square into n minus 1. Hence the required result.